Welcome to solverfy.
This question asks us to take a look at utilizing our handy-dandy periodic table and determining some periodic trends, in particular, periodic trend for atomic or ionic radius. We're going to use a couple of principles here to help us, and that is, in general, as you move left to right across the periodic table, we see a decrease in atomic radius, and as we move top to bottom, an increase in radius. In addition, when we compare a cation to an atom to an anion of the same species, the cation's the smallest, followed by the atom, and the largest of the three will tend to be the anion or the negatively charged species. So let's use those ideas to explain um, how and why we see the trends that we do in these answer choices or these questions. So why is it that the iodine ion is bigger than iodine as an atom, which then is bigger than the iodine cation? If we look at where iodine falls in the periodic table, ooh, I should not use yellow for a color there. That is not good. Let's try that. It's element number 53. So that means that it has 53 protons to accommodate a certain number of electrons. In its atomic form, it's going to be accommodating the same number of electrons as it has protons, 53. In its cation form, it's going to have one less electron. And obviously, in its anion form, it's going to have one greater electron, or 54 electrons. So if we look at it this way, when we have a nucleus containing protons, their job is essentially to hold the electrons in their shells as close to the nucleus as is possible. Now, that's an easier job to do when we have fewer electrons to take care of. There's a greater pull or attraction toward the nucleus when we have less interaction between the electrons, and a greater ability then to hold a fewer number of electrons in place. I call it the babysitting effect. When we have a fewer number of kids to babysit, it's a lot easier on us than if we have more kids to babysit. So if a nucleus has fewer kids or electrons to take care of in a positively charged form, it's going to be easier for it to hold those electrons close to itself, and therefore the smallest species that results from that babysitting effect, if you will, is always going to be the cation. The anion is always going to be the largest because there's more kids to take care of, and it's more difficult for protons to hold a greater number of electrons toward itself. So they're allowed to wander a little bit more, and that results in a larger overall species. And when we compare the calcium, magnesium, and beryllium 2 plus cations, they're all in the same family. And the trend that we see for atomic radii holds true in this sense for these ionic radii as well. That calcium 2 plus, magnesium 2 plus, and beryllium 2 plus should increase in size as we move down the table. So calcium is the closest to the bottom of the family. It should be the largest of the species. It has the most shells surrounding it because it simply has more electrons. Whether it's in its cation form or atomic form, it's going to have more electrons and shells than either magnesium or beryllium. So whether we're talking about a cation comparison or an atomic comparison, calcium, because of the greatest number of shells of electrons, will always be the largest, just as it is in its atomic form, followed by magnesium, and finally beryllium with the fewest shells is going to have the smallest overall size. In the final example here, we're comparing iron. Again, this is pretty similar to what we saw in example A. Iron is element number 26. So in its atomic form, it has 26 protons to take care of an equal number of electrons and hold them fairly close to itself. That's cool, but when it becomes iron 2 plus, now it has two fewer electrons. Babysitting effect again. Um, we now have fewer kids or electrons to have to account for, so the remaining electrons that are there are capable of being held more closely to the nucleus, and that results in a smaller size for iron 2 plus as opposed to its atomic form. And finally, iron 3 plus, the even more positively charged cation, is going to be the smallest of all because it has the fewest number of electrons for that same nucleus or same number of protons to have to account for. And iron 3 plus, the iron nucleus, is able to hold those remaining electrons even more tightly or closely to itself. And that results in iron 3 plus being the smallest of all the species here.